All right, welcome everybody to the last talk of this evening for the Michigan State University Science Festival. My name is Roxanne Truen and I'm the coordinator of the festival. And tonight I'm joined by Dr. Zach Constan, who's the outreach education coordinator for the facilities for Rare Isotope Beams and the National Superconducting Cyclotron Lab. Did I get it right?
I mean, there's a lot of words and they're big, but that is all correct.
Awesome. So Dr. Zach is going to talk to us about fantastic nuclei and where to find them. And as he's talking, if you have any questions for him, you can enter them in the Q&A section if you're on the Zoom webinar. And if you're on Facebook Live, you can enter them in the comments section. So with that, I'll let you take it away, Dr. Zach.
Totally. Thank you, Roxanne. Welcome everybody. Thanks for tuning in, spending your Thursday evening with us. I appreciate you taking the time. I want you to know that my kids are downstairs watching Star Wars and I chose to be here with you. So you're important. But of course the MSU Science Festival is important. I love doing this every year. It's a lot of fun. And you get to meet a lot of cool people like you. I'm so sorry I can't see your faces this year, but that's, all right. We will make do. Maybe next year I see you. But just to remind you, this is an official MSU Science Festival event, one of over 200. And this is just the first of 4 for me. So I hope to see you maybe at the other ones. We have lots of different ways that we like to talk about what we do. But tonight I'm going to be very specific, covering what we do in our laboratory. Let's pull it over. There you go. About how we make the nuclei, basically the accelerators, the collisions, all the exciting stuff, right? Things hitting other things really, really fast. That's what you tuned in for, and I'm glad, right? We get each other. We're on the same page. So, talking about fantastic nuclei and where to find them. This is totally my own title. I did not crib it from anything else. There's no copyright infringement at all. So, again, I'm Zach. That's one of my favorite things about doing all these things on Zoom today, these days, is that I always know everybody's name because it's right there under there. Anyway, so you know me, I'm Zach. So let's talk about it. Michigan State University is a wonderful place. There's a lot of wonderful research going on there, and hopefully you'll tune in throughout the festival to learn what other people are doing. But in my opinion, the best stuff going on at MSU is in this building in the middle of campus, and it's called the Facility for Rare Isotope Beams, or FRIB. I know it looks like FRIB. It's pronounced FRIB. Just trust me on that, okay? I promise I should know. So what we do in this building, and this is like a city block, this thing is really, really big. We study the nucleus of the atom. Over here we have sort of a model atom. This is what people often think of, they recognize when they're talking about atoms. Of course, real atoms are very, very small. You can't see them. The best microscopes on Earth can barely get some sort of evidence that the atom is there. But of course, this is not what a real atom looks like. They're not red, white, and blue. Sorry, America. But it's just a nice model. And we can just think about the atom as being like this, made of protons, neutrons, electrons. But of course, the protons and neutrons form the core at the center of the atom, and that is called the nucleus. And at our laboratory, FRIB, we want to study the atomic nucleus. We are nuclear scientists. That's our business. Electrons are nice. We just don't care. Okay? So we're going to be into that kind of thing. And we don't just want to study any old nuclei. You've probably seen the periodic table. It's nice. It lists all the elements that we know. And there are lots and lots of them. Carbon, very famous one. You are carbon-based, I assume. And of course, carbon actually comes in multiple varieties. It's known as isotopes. Some are common, some are rare. So the real issue that we're dealing with at FRIB is we don't want to just study common nuclei, the kinds that you and I are made of, that this wall is made of, that this computer is made of. We got lots and lots of common nuclei lying around, but we don't have the rare ones. And that's our business. That's what we want. So how are we going to get fantastic nuclei, right? That's the whole point of this talk. So periodic table, no offense chemistry, but this just doesn't have enough detail in it. So I feel like I need something better. And we have constructed something better in nuclear science. It's called the chart of the nuclides. As you can see, the boxes are really tiny. So it's obviously better. Look how tiny those boxes are. We're going to zoom in. It's just a sort of graph. Number of protons determines your element, and that's on the vertical axis here. So if I've got 1 proton, the element is hydrogen. Great. If I've got 6 protons, element is carbon. There's your carbon. But of course, this nucleus, which has 6 protons, could have different numbers of neutrons. And that's what an isotope is. It's just, how many neutrons does it have? If it has, this many neutrons, so you see all these squares here that are black. Those are specific isotopes of all these elements. They have this number of neutrons. And those particular isotopes are stable. We call this the value of stability, which is a great name for it because they're very low energy. That's why they're stable. They are not radioactive. That's why they're stable. They are common on this planet, right? So like, go ahead and look at any direction right now, and you are looking at stable, common nuclei. And because we have them all over the place, they're boring. Well, from our perspective, like you're not boring, right? This is all not that boring. This is really interesting stuff. But FRIB wants to study rare nuclei. So not these, not the black squares. If it's not a black square, all these different, pink diamonds, blue circles, purple horseshoes. We don't actually have any purple horseshoes. That's Lucky Charms. But all these different symbols represent different types of radiation. These are all radioactive nuclei. And for that reason, they are rare. They have a short lifetime and you just generally won't find them. So like all the stuff you're looking at, almost none of it will be rare nuclei. There just aren't any lying around. Well, they do not lie around on this planet. They do occur in stars. Stars make these kinds of things all the time. You want to talk about fantastic nuclei? Yeah, stars. And for this reason, right? They're radioactive. We don't have them, but stars make them. They're awesome. Okay. So FRIB, not interested in studying boring nuclei. We only want the fantastic nuclei. So this is the kinds of stuff they were interested in. Nuclei with half-lives less than a second. That's good stuff. It's really interesting stuff. So yeah, that's what we want to do. Guess what? It's not easy. That's of course why we need big, complicated, amazing laboratories to do this kind of research. So how are we going to study fantastic nuclei? We will start with the ones that we have, right? So I will just grab this flashlight, which is full of nuclei, and I'm going to start with this thing, which is stable. There's a whole lot of normal boring nuclei in it. And then I'm going to smash them very hard. Essentially, if you can take a nucleus and you can break it, you can knock off some protons and neutrons, you change what it is. You can change it from something that is a combination, a specific isotope that is stable and boring, and you can make it possibly something fantastic, which is good stuff. Thomas has a question. I can see it here, and I'm going to answer it right now. This is a great question. Yes, there are lots of different kinds of radioactive decay, and as you can see, there's a pattern essentially. There's all these blue circles here. Let's go back for a second. Too many things. Okay, all the blue circles here. That's beta minus decay. All the pink diamonds is beta plus. So essentially, the way that a nucleus decays depends on how much excess energy it has and how fast it can get rid of that energy by decaying. So there's ways that are easy to decay and there's ways that are difficult to decay, but might become more interesting and useful if you can lower your energy very, very quickly. So when you look at these particular nuclei here, these actually chuck out a proton. It's pretty rare for a nucleus to do that, but because they can essentially get to something very low energy very quickly, that is why they do that. Beryllium-8 is actually not that high of an energy, but by doing alpha decay, by literally chucking out a helium nucleus, it can turn into 2 helium-4s, which is so much lower energy that it's actually favorable for that particular nucleus to decay in that way. Thanks for asking, Thomas. All right, moving on. So we break nuclei, and I actually brought a little demonstration for you. Here's my nucleus. I just can't talk about this stuff without toys. It's easier. So let's just imagine that this nucleus is made of protons. They're the yellow marbles, and neutrons, that's the green marbles. It's just magnetic marbles. It's a lot of fun. So imagine this is what a nucleus looks like. Now, if I want to change this nucleus, what I've got now is 6 protons, 6 neutrons. That is carbon 12, which of course is the most stable and common form of carbon in the entire universe. You're chock full of it, 99% of your carbon. Here we go. I will now pull off a single neutron. It's still 6 protons, still carbon, but now it's carbon 11 because I removed 1 neutron. Now, this is pretty easy with my fingers. You cannot reach into a nucleus and pull out neutrons. I am so sad to report. As good as you might think you are with tweezers, no one is going in and pulling out individual particles from a nucleus. So how are we going to change to carbon 11 or some other fantastic nuclei? Easy. Take the stable ones, smash it really hard. Literally, we hit the nucleus so hard that it knocks off some combination of protons and neutrons and changes it to something else. So literally, if I threw this against the wall, I'm not going to, you could make fantastic nuclei. That's where we get them. You know, stars make them, but like it's just not safe to go to a star. Sorry. So we smash nuclei and study, hopefully, the rare fantastic ones that are left over. Oh, Tyson has a question. I like this. 1 proton is hydrogen. What is 1 neutron? 1 neutron is a tiny, tiny, tiny neutron star. Yep, that's all it is. It's not an element because it doesn't have any protons in it. However, this is a fun fact. A neutron by itself is radioactive. In a nucleus, it's fine, but but outside of a nucleus, it will decay to proton, so become a hydrogen, you know, with a half-life of about 10 minutes. Seriously. Weird stuff. Okay. Anyway, moving on. So this is our lab. It's a wonderful lab. And for the last 50 plus years, we have been using cyclotrons that are 5 stories tall. We've got 2 of them, and one's bigger than the other one. Essentially, this cyclotron accelerated nuclei, stable common nuclei, with 60,000 volts. Never touched that, obviously. And it got them going 30,000 miles per second. If you want to break the nucleus, you have to hit it really hard. But then we came out of this little cyclotron, this is only 10 feet wide, 5 stories tall, went to the larger cyclotron, which accelerates with 140,000 volts. Just, you know, I can get it going even faster. And that'll get you up to about 40% of the speed of light. So if you can make a nucleus go that fast and run it into something else, another nucleus, you're going to break it. It's called fragmentation. I'll show you. So we've been using cyclotrons to do this, to break boring nuclei and make fantastic ones. That's nice. 50 years of cyclotrons, we're pretty good. Okay. I don't know if you know anything about science. I mean, you're at the science festival, but here's a lesson you should take away. There is no such thing as good enough in science. There will never be okay, we're done. Probably there's more questions to answer. That's what I love about it. So our lab, and this is the kind of the map of the building. Our lab has this space with the cyclotrons, and that space is 450 feet long. It's a big room. And we've been using these cyclotrons or something similar for the past 50 plus years. Well, if you want to study even more fantastic nuclei and discover more things nobody's ever seen, et cetera, you got to improve. Our laboratory has constantly been improving over the last 50 plus years that we've been around. If you've been around campus at all and been by the lab, you might have noticed we're under construction a lot. And a lot of people, maybe that's kind of not convenient for your, walking around campus. But yes, we're always under construction because we're always improving. Well, this lab is honestly one of the top 3 in the entire world for studying rare isotopes, and that is not good enough. So here's what we're doing. To break more nuclei, we are building the facility for rare isotope beams, right? So what we've had was the cyclotron laboratory. That's what everybody knows us as. But we're changing our name because we're changing. FRIB is a $730 million project. Most of that money is from the US Department of Energy, Office of Science. They are sponsoring this project. Some of the funding comes from the state of Michigan and a little bit from Michigan State University because they appreciate that kind of thing, obviously. But with this funding, we are going to replace two of the best cyclotrons in the world with a 400-yard long linear accelerator, 35 feet underground. That new accelerator is really going to do a few very important things. Number one, it's going to accelerate those nuclei to twice the energy. So literally, we're going to smash harder. But more importantly, it's going to accelerate hundreds of times as many nuclei per second. Now, if I threw this against the wall, I would make something new. Would I make something fantastic? Maybe. I got a good chance. Would I make exactly what I wanted? Like if I seriously wanted to take one neutron off this thing and make carbon-11, what are my chances of doing exactly that, throwing this against the wall? It's terrible. What if I threw 1 billion of these against the wall? Now we're talking. Okay, that's what the cyclotrons have been doing, actually. 1 billion nuclei per second. This is going to do hundreds of billions per second, which means break more nuclei and you have far better chance to make all different kinds of fantastic nuclei. So this is going to have access to, essentially, a whole lot of isotopes nobody's ever seen before. I forgot to tell you. When I showed you that chart before, the chart of the nuclides, it lists over 3,000 known isotopes. It's a lot. 60 of those isotopes have been discovered at our laboratory so far. Not bad. The last time we discovered a new isotope, we all got free pizza. It was a big day. So I was excited, obviously. They feed us when we do good. I mean, when you work at a university, free food is a very powerful motivator. But anyway, it's only 60 of the 3,000 were discovered at our lab. FRIB will discover probably 1,000 new isotopes. And that is a lot of free pizza, if you think about it. So we'll have access to nuclei nobody's ever seen. We're going to be able to do experiments nobody else can do. Therefore, we will be the world-leading rare isotope facility. When this is done, 2022. Hey, less than a year from now, we should be running the best rare isotope facility in the world. Knock on wood, nothing goes wrong, but like we've been building this thing since 2014. We're so close. And I'm going to show you a lot of detail about this. That's why you're here. That's why I'm here. But the way it works is it's a linear accelerator. It goes down a straight line, turns around, accelerates again, turns around. So it's basically one long straight accelerator, but it's folded a couple times. So it'll fit into the space, basically. So coming out of this accelerator, which is 400 yards long, we hit the target at about half the speed of light. That is 4 times around the Earth per second. Not bad, not bad. So we break the nucleus. At this point, this is 60 feet underground. Then we bring the nuclei up out of the tunnel and connect them with all the detectors and things we already have, we've been using with the cyclotrons. They still work, so it'll be fine. So we're going to be able to reuse all the experiments we've been doing. So let's get into the details. This is a cutaway view of the whole linear accelerator. You start on, basically ground level. So if you ever walk down Wilson Road, you can see this thing. You'll see this nice big building, and inside that building, there's the ion source. So that's where you start with some stable, boring nuclei. You ionize them, which means you're just knocking off electrons. Then you send them down into the tunnel, and they accelerate through this first bunch of boxes. And I'll show you more about those boxes in a sec. So once you get to the end of this and you turn around, they're going pretty fast. Not really fast, but pretty fast. Then you accelerate again down this line. You turn around again. It's faster. Surprise. And then, of course, you go through the last group of boxes. Now you're going even faster. And you head off to the target. At this point, half the speed of light. Not as fast as, say, Fermilab or the LHC at CERN. They get up to almost the speed of light, but for our purposes, you don't have to smash quite that hard. It's fine. So this is going to smash half speed of light, and that is perfectly sufficient for breaking the nucleus. So that's pretty good. Here's a good question from Thomas. How do you preserve the momentum as of nuclei? So this is an important point. In what you're used to in real life is that when you turn, you lose energy, right? Now, of course, when you do it in a car, it is really because of friction. These nuclei traveling down these pipes, and they are in a pipe, they're under vacuum. There is no air in that pipe. So number one, there is nothing for the nuclei to run into. So we're not going to lose any energy that way. Basically, what makes these things turn around, so you're changing the momentum, but the energy is the same. What you have down here is giant electromagnets. In fact, almost everything you see on this, there's going to be electromagnets everywhere, because that's how you steer nuclei where you want them to go. So there you go. That's how it is. And I'll show you more as we go.
All right. And Dr. Z, we have another question that came in from Ted. He wants to know, where does the linear accelerator fit in relation to the Higgs boson papers from a few years back? He says he's a layman, so he wants to.
Sure. Yeah, the Higgs boson is where the news was, right? It was the hot stuff. And of course, they built the Large Hadron Collider at CERN in Switzerland, really, because they just couldn't discover the Higgs boson based on what they were predicting. They needed something bigger. Now, the Large Hadron Collider is a circular, it's a ring, accelerator. It's not straight line, it's a ring. Well, it's really just, it's a long story. But yeah, that thing is 17 miles around. It's big. It's really big. This is 400 yards long. So not nearly as big. However, we're doing something very different. We're accelerating very heavy ions. They can do heavy ions, big nuclei over there in Switzerland, but they more often are doing protons, just accelerating protons. And that's something you can do. Cool. So thanks for asking. So this accelerator is not nearly as big as some other ones you've heard of, but it doesn't have to get to quite the same energy. Even so, for heavy nuclei that we're accelerating, this is a really high energy, and it's more of those nuclei, heavy ions, than anybody else will be doing. That's why we're excited. Smash more things. That's what's important. And so down in the tunnel, what you see is a line of boxes. And these green boxes are called cryomodules. They're called cryo because all the accelerator parts inside need to be very cold. And we're talking 4 Kelvin. If you know absolute zero, these are 4 degrees above that. That's minus 450 Fahrenheit. It's pretty cold. We use liquid helium for that purpose, which gets the job done very nicely. We use more liquid helium than probably anybody else. Maybe in Michigan, I don't know. It's a lot of liquid helium. We make it ourselves, by the way. We have a plant where we just, because it's expensive. Well, anyway, the point is you're keeping stuff cold. What you're keeping cold is these cavities, cylinders, maybe this wide. We have different sizes and shapes, but these ones are like this wide, maybe, 4 feet tall. And these accelerator cavities are what's actually going to accelerate the nucleus. They just have to be kept very, very, very cold because they're superconducting. Essentially, if you can make them cold enough, they have no resistance to electricity. You probably have some experience with resistance because, when you use electricity, things get hot. Basically, copper wire, silicon wire, as you're running electricity through, the resistance converts electrical energy into heat, which is a waste, right? I'm actually trying to heat my ear. I want to talk on the phone, but I end up wasting some heat. So that's not so great. But these are superconducting, which means no resistance to electricity. And they can charge to really, really, really high voltages. So this is what it looks like on the inside, sort of a cutaway. There's an outer cylinder and an inner cylinder. And there's a couple gaps in between the outer and inner. We can create a 1,000,000 volt difference across that gap. Now, the fact that we can do 1,000,000 volts and not get lightning between those two surfaces is really good. but no lightning. So you can create this incredibly high voltage difference. That's what actually accelerates the nuclei in a beam through those holes. So they come in one side, and when they go out the other, they're going faster. That is an accelerator for you. So that's pretty great. Well, what if we just put a whole bunch of these things in a row? Makes a lot of sense. So that's what we've got, basically. One of these boxes could have 8 or 10 of these cylinders. It varies. And, again, your beam, your nuclei pass through all of them, and they come out going faster than they were going in. And Thomas is asking, how fast do they come out? When they come up out of that tunnel, half the speed of light. That's the thing. Of course, we have 3 legs. After the first, after the second is not quite yet half the speed of light. I don't know how fast it is after the first and second legs. I'd have to look it up. So sorry, I don't have more. But really the beauty of a linear accelerator, actually, I think I got it on this next slide. How do you choose your accelerator? We've been using cyclotrons for 50 plus years, and now we're using a linear accelerator. Well, why would you do that? Though there's good reasons to use one over the other. Circular accelerators have been really popular for a very long time because essentially your nuclei are going around in a circle, and you can reuse the same accelerator over and over again to kind of kick it up to a faster and faster speed. Because you're reusing the same accelerator, it's cheaper. That's great. There's certain advantages, right? There are some problems with that, though. So this beam, this red line here, is all nuclei. Nuclei are positively charged. They have protons in them, which means the nucleus here is pushing on the nucleus here, is pushing on the nucleus here. Essentially, if we pack too many nuclei in there, and they're all positively charged, they push each other into the walls, and then you lose them. So that's a problem. There's definitely some serious issues with circular accelerators. They're cheap, they're effective, and they're great, but people are kind of getting away from them. They're getting into linear accelerators now because here's some advantages for you. Here, my beam, instead of going around a circle in this small confined space, it's just going down this pipe. And so the nuclei here are far away from the nuclei over here. They're not pushing on each other. So I can pack more nuclei through. I can smash more nuclei. And that's, of course, what we want. So that's a pretty good deal. And one of my favorite things about it is if you want to go faster, if you want to get your nuclei going a little faster, give them a little more energy, just add a few more of those cylinders, those cavities on the end, and you can go faster. It's oversimplifying a little bit, but yeah, it's possible. The disadvantage of a linear accelerator is instead of reusing this over and over, I got to build a whole lot of accelerators in a row, and it is more expensive. And we have to use much higher voltages. But for our purpose, we've done pretty much what we can do with cyclotrons. To do a better job with FRIB, we need a linear accelerator. So that's how we picked it. That's what we did. Good, yes. So Thomas asks again, yes. Overall, our linear accelerator is more conducive to long-term improvement plans like MSU has because they're modular, and they are, and that allows for modifications. That's true. Okay, I got to show you something. Oh my gosh, this is so exciting. I wasn't even going to bring this up, but now you brought it up. So we've got 3 legs on this accelerator. First leg, second leg, third leg. You can see these blue boxes. They're actually green, and this is just so it's easy to pick them out. But so those boxes for accelerating. You might notice those boxes stop, and there's no boxes right here. All you got down this little leg is some magnets for focusing and steering your nuclei in the right direction. So no accelerators. We left some extra space because if we get a little more funding in the future, we can add more accelerators and get up to even higher energy. So a linear accelerator is wonderful because it is able to be added onto. You're right, Thomas. You pretty much nailed it. Okay, so fun stuff. Linear accelerators have a lot of advantages. but most importantly, we can smash more nuclei. And that's what we want to do. So we're doing it. Here's a little animation. Shows you nuclei shooting down these beam pipes in the tunnel. And then they come over. Next step, of course, is to smash them into a target. Here's a nucleus, looks like it's made of marbles. And it hits the target, which is just a chunk of material, really. And it just changed. And you can see when they come out of here, they've changed. They're missing some protons and neutrons, and they're also excited, so they're wiggly. Now we've made some fantastic nuclei. We need to filter out the boring ones. And so what we're here, this is what we're looking at is a magnet. A magnet basically steers the nuclei we don't want off to the side and steers only the fantastic nuclei we want to study, out the other side, essentially. Oh man, these questions are so good. Look, I give a lot of tours and talks and things. A lot of the groups are like fifth graders, and I love fifth graders. They ask really fun questions. But these are a little more specific to the physics, and I love them. So thank you. Just want you to know. Could you expand the size of a circular accelerator in width to separate the beams from each other? Totally true. You could make a much bigger accelerator. The problem is, the bigger it is, the harder it is to keep the magnetic field strong enough inside of it and even enough across the entire area. So there are other technical challenges that get in the way when you want to go to much larger, sizes. It's true. The target, what is the target made of? The target we've been using is beryllium, element 4. The new target is going to be carbon. It's a rotating disk. And the nice thing about that is we're hitting this disk with more nuclei than almost anybody else. It's just really heavy stuff. It's a lot of damage. It's a lot of heat generated. So when the beam hits that disk, it rotates. Then that beam can hit another spot. Well, this spot rotates over here through a cooling section that'll pull the heat away. So then our beam won't destroy the target, and we can keep going with our experiment. Very important. Okay, so how we smash nuclei? Whole lot of nuclei, stable isotopes, something boring. Billions of nuclei per second. In this case, oxygen 18, but it could be anything stable. Of course, our target has been beryllium. I did mention that. And if you literally have to hit a nucleus in the material. Like, nuclei are small targets. The only way to break a nucleus, in this case, is really to hit it on another nucleus. Your chances are not very good. In fact, they're so bad that most of the nuclei don't hit at all. They come through unchanged. But some of them do hit something, and they change to something, hopefully, fantastic. Depending on the experiment we're doing, depending on the specific rare radioactive isotope we want to study, we might get 1 nucleus per second out of the 100 billion that we actually want. 1 per second, or maybe 1 per half hour. We've done an experiment like that, or maybe 1 per week. There's a lot of different possible. Oh my goodness. Yeah. Thomas is asking about how we rotate that target. I am actually not sure how that, if it's attached to an axle or not. I mean, in the end, as long as that axle's, as long as you're hitting it off center, just the target will get in the way. Hopefully that'll be the case. I will have to find out. So thanks, Thomas. I will check it out. Hopefully next time you see me, I will know.
And we have another question for you from Melissa. She wants to know, how does the magnet know which nuclei are fantastic when they're filtering?
Okay. Melissa, you are totally setting me up for the next slide. Give yourself a gold star, okay? So here's how we do it. Basically, we are separating the nuclei with magnets, and you have to do it a very specific way. So as nuclei pass through a magnetic field, they turn. It's just because they have positive charge. So essentially, we know what fantastic nucleus we want to study. In this case, let's just say carbon-16. That's an example. So essentially, we can tune the strength of the magnet so that only carbon-16, pretty much, will make a 45-degree turn and escape out a little opening on the other side. Pretty much all the other nuclei, and especially all the boring ones, either turn too little or too much and end up literally hitting the wall of the magnet and just sticking there. They just sit there. So we literally can tune the strength of this magnetic field to select out the nuclei we want. And so this is the beauty of the whole system. It's really quite clever. You've accelerated something stable, oxygen 18, and just a whole lot of them to about half the speed of light. You hit the target, boom, you break it on the carbon. You make, really, if you do this enough times, you make everything. Just about every possible combination you will eventually make. Maybe not a lot of them, but you'll make some of them. So literally, if we smash a whole lot of oxygen 18, we get some of all of these, which means we get at least a few of what we want, carbon 16. We have 4 of these magnets here for the turns. There's actually a couple new ones being added for FRIB. But these big magnets, again, steer the nuclei, they make a turn, and so, they turn just the right amount as we tune these up to the right strength. So essentially, if you've got a rainbow of different isotopes, it's just a nice way to think of it, coming in, after each turn, you've gotten rid of a few of them until you've just got the one color, fantastic nuclei, that you want to study. Just, woo. And they're doing this, they're filtering out the garbage nuclei as they travel through at half the speed of light. If you've ever heard of a mass spectrometer, chemists use those to separate elements all the time. This mass spectrometer is 35 meters long. It's a big one. Good, okay. Sriram is asking, does this work with the same principle as the Rutherford gold foil model? Yeah, the fragmentation of, actually, you have to get a nucleus close enough to actually run into another nucleus. With the Rutherford's experiment, which discovered nuclei in the first place, they weren't coming in quite so fast. So really, just because they were both positively charged, the nuclei that they were trying to hit and the ones that are coming in, they kind of bounced off and they went in different directions. So if Rutherford could have gotten to a little higher energy than he had, he could have actually done fragmentation, just like we're doing here. No kidding. So good question. How do you, oh man, this question. How do you strip off the electrons off of your atoms to create the ions? You have to get rid of the electrons first. We have what's called an ion source. And basically, the short answer is you take an atom, nucleus with electrons around it, and you hold it in a magnetic bottle. That is what they call it. And you shoot electrons at it. So electrons are coming in, and because they're negatively charged, the electron out here is negatively charged. It gives it a push, it excites it, maybe enough to actually knock that electron off. So seriously, by shooting in more electrons at pretty good energy, you can knock some electrons off and ionize, basically give yourself a charged nucleus. We can't remove all the electrons for most elements, but we can get rid of most of them. Good question. Yes. Thomas is right. So the larger ions turn too little. So yeah, so there's basically 2 factors here. And I kind of glossed over it. You're right. But here, I'll give you a little detail. 2 things affect the amount of turn, the amount of deflection that you're going to get on your nucleus. The more massive it is, the less it's going to turn. That makes some sense because it's harder to push. But the more charge it has, the more protons, the more that your magnetic field is going to affect it. So it's not just the mass, it is the ratio of the charge to the mass. So we are basically tuning the magnetic field strength to pick out a specific charge to mass ratio. There you go. Nice. Can some of the, oh man, look at this question. Thank you, Anonymous. Can some of the isotopes decay before you can study it? Yes. Okay. So here we go. We made the nuclei. We made something rare and radioactive. Awesome. And let's say it's super duper rare and it's super duper short lived, but it's going half the speed of light. So the time it takes to travel to one of our detectors where we can actually make the nuclei we want or study the nuclei, the time is about 1/millionth of a second. So most things will last. Some things won't. And so in those cases, you actually have to make something longer lived, and then later on, right next to your detector, smash it again, and hope to make something that's really, really short-lived. And I'm talking a millionth of a billionth of a second or less. It will still decay, but then like all the pieces from that decay, the daughter products is what they'd be called, you can pick them all up. And based on the evidence of those things, you can tell more about what the original nucleus was like before it decayed. Okay. I'm supposed to be done at 8:30. Isn't that right, Roxanne? I am I'm going really
Yes, that's true.
well. Okay, I'm going to try.
You're the last one, so if you need to go over.
Well, that's good because I always go over. I think I'm sure you all know.
That's why we put you on last.
Smart. Okay. Well, I'll try to wrap it up, but I do want to make sure all your questions get answered, as many as I can. So we smash nuclei at about half the speed of light. We do make fantastic nuclei that really you would only normally find in stars, except they're now traveling at half the speed of light. That's way higher energy. You never find that kind of stuff in a star. So it's not quite what we want. And this is what the cyclotrons look like, by the way. This is what they look like on the inside. So cool stuff. So here's how we solve that problem. So we got to we get to ionize, just like you asked. We got to remove the electrons. We got to accelerate to half the speed of light, because you have to go that fast to break the nucleus when you hit the target. But now it's going too fast. So we got to separate out the garbage, keep the ones we want. Now we thermalize, which means we slow the nuclei back down nearly to zero speed. They're almost stopped. And then we ionize them again, remove the electrons again. Then we get rid of the junk again, and then we send them to a smaller, shorter accelerator that only goes like 8% of the speed of light. We don't need to go nearly as fast because we're not going to smash them again. We're not going to break the nucleus. All this is doing is taking a star-like nucleus and giving it the right energy to act like it was in a star. Just 8 simple steps, guys. Make nuclei that act like they're in a star. It's totally going to happen. Totally going to happen. Okay, so we have a little extra accelerator to do that. In fact, we're the only place in the world that can. So that's kind of nice. And then we want to literally measure nuclei acting like they're in a star, but you can't see them. We have a variety of detectors for measuring. So coming out of this little accelerator, they're moving at the speed you would see in a star. You can send your nuclei into this other room, into a variety of different detectors to measure the nucleus. And here's how you actually do that. You're never going to see it. The best microscopes on Earth will never see the nucleus. You need to have some material or equipment that will react to the nucleus in a way you can observe. This is a piece of plastic. It's a nice plastic. It's fancy plastic because it's called a scintillator. When nuclei hit it, it glows purple. So can you see the nucleus? No. Can you see purple light? Yes. And that's how we detect the nucleus without ever having seen it. This also works really well for ultraviolet or black light. So there you go. Now I'm detecting UV rays. But yes, seriously, this thing glows like this when nuclei hit it at the speeds it would see in a star. So when the light comes out, that is evidence you can use to say, aha, I can tell you something about that nucleus based on the light coming out. And we have other detectors that the nucleus hits it and you create a small amount of electric current. Well, that's something we can totally measure. We're very good at that. So that's how all these detectors work. And the kinds of things we're literally trying to understand with these experiments are, no kidding, where did all the nuclei in the universe come from? Somewhere. The Big Bang pretty much only made 2 elements. So at the beginning of our universe, about 14 million years ago, we really only had the 2. And that's why to this day, you look out in the universe, we have more hydrogen and helium than anything. Stars do fusion, which makes heavier nuclei. And so the carbon you're based on, the oxygen you're breathing, the iron in your blood, the calcium in your bones, they were made in stars. Right? And if you want to understand that process, you don't go to the star, you study nuclei acting like they're in a star, fantastic nuclei in our lab, right? But there are a lot of elements that can't be made through fusion We think that when two neutron stars merge or a star explodes, a supernova, we think that's how you'd actually make some of the most, well, you make very unstable, rare isotopes. Hey, that's what we study. And when they decay, they become the elements, gold, lead, silver, uranium. Great stuff. And we're pretty sure these are the only places they can be made. So the fact that we have them at all, we think that's the culprit right there. But how do we know? Again, we're not going to go to a neutron star. We need to reproduce the nuclei doing this kind of stuff. And so what I've got here now, this is a theoretical simulation of what would happen in a supernova. I'm going to show you how a supernova could make very rare, fantastic nuclei. So we're going to start with some iron. The red dot here, basically this is an isotope. If you have red, that means a lot. Blue is not very many. But in a supernova or a neutron star merger, we believe there might be lots of neutrons flying around by themselves. And when they run into a nucleus, they just kind of stick on. So we add extra neutrons onto a nucleus. So it'll add neutrons, but it's also going to decay because it's radioactive. So at some point, it's going to decay and it's going to add neutrons to decay. So I'm going to show you the series of reactions according to this theoretical model of what would happen in a supernova just exploded. So the time here, time actually tells you how much time has been since the star exploded. And the temperature is 1.5 gigakelvin. That's how hot it is. Let's let it run. Within 1 second after the supernova explodes, we predict that all these isotopes could be made. You see the black squares are the stable ones. So all these are fantastic. They're very radioactive. They are rare. And we think that a supernova can make all these. They're eventually going to decay back and make some of the heavier elements we talked about, gold, lead, right? But let me tell you, we can't observe this going on in a real neutron star merger or supernova or whatever. So there's a lot of nuclei out here we need to study, try to understand this process of how you can make heavier elements. Well, here's another chunk of that chart of the nuclides again. This shows you all the different isotopes that our laboratory, the Cyclotron laboratory, has been able to make and study over the last 50 plus years. It's a lot. It's like 1,000. Pretty good. You see these red lines over here. This is the path. We call it the R process. This is the path of isotopes that we believe a supernova or a neutron star merger would make to do that, that creation of heavier elements. As you can see, we can't make a lot of those. And in fact, we can't make most of them. And this goes on beyond here. This is what we've done with cyclotrons. But with FRIB, this is what we're going to have access to. So you can see this path, the R process. Yet some isotopes, really fantastic nuclei, we still will not be able to make. But the majority of them, most of them, FRIB will have access. For the first time ever in the history of humanity, we'll be able to actually measure these nuclei and use that information to try and put together our understanding of how the heavy elements in the universe were made. That's what we're looking forward to. That's the excitement about FRIB. And there are 1,500 scientists all over the world that cannot wait for FRIB to start because that's where they're going to do their experiments. That's what they've been looking forward to this whole time. So, and that's where they all come from. I just need to add this. This is really important. Before you go, who cares? I mean, you're at the science festival. I might not have to sell science to you, but there better be a good reason for this kind of work. In the process of studying nuclei, like we do at our lab, even nuclei that are rare and radioactive and you would not find on this planet, we are understanding the nature of the nucleus and matter itself. Everything's made of matter. So the things we learn literally contribute to medical imaging, MRIs, PET scans, cancer therapies, geophysics, basically looking at the nuclei in an object and telling how old it is. So carbon-14 dating, you might have heard of. Electricity, 20% of the electricity in this country comes from nuclear power. Smoke detectors in your house probably use radioactive material. And that's based on what we've learned. And of course, my favorite, this technology here, you really can't build solid state electronics this small without the last 50 years of basic nuclear research. The things that we've learned in nuclear science made this possible, right? Now, are we trying to make phones? Are we trying to make, MRIs? No, we're trying to understand the nucleus. But in the process, we learn things that are incredibly useful to a lot of people. So what we're really doing in nuclear science is saving lives and changing the world. Who cares? Everybody cares. And that's why this is funded by the government. That's why state of Michigan, Michigan State University, we invest in this kind of research, cutting edge, bizarre stuff, because we know it is going to lead to big changes. It's going to make a difference. That's why we do it. Okay, so we're building that FRIB. It's almost done. It's getting really close. It's brought a lot of money and jobs to the state. I like that. But in the end, to me, what's really, really important is we're going to be doing the best rare isotope research in the world. We're going to have a lot of really cool people around here. And in fact, when you have a really big project like this and a lot of really brilliant people inventing new things, it creates new businesses. The Lansing area has 2 accelerator companies that spun off from our laboratory. People who worked at our lab left and started their own business because they could build and sell accelerators. No kidding. So that's kind of cool. So there's another good reason to do this kind of work. Economic growth. Shocking, I know. So the whole point of this talk, there's a lot of fantastic nuclei. Stars are making them. Supernova exploding. Neutron-star mergers. Just a lot of really beautiful animations. We can't go to any of those, at least not safely. You can observe them from afar, that's great. But based on those observations and the new fantastic nuclei we can make and study at FRIB, we can literally learn and understand what's going on in stars. So if you love astronomy, we're doing it just inside this building, and it's a smaller scale, safer. So that's FRIB. It's a fantastic place. If you want to learn more, we've got more things throughout the festival. I got 3 more events. Look us up in the schedule. You can also go to our website, nscl.msu.edu/public/learning. There's a whole lot of resources there. There's YouTube videos. There's activities you can do at home. There's a video game. I'm not kidding. If you want to smash nuclei on your phone, that is an option. Okay, I only went 8 minutes over. That's not bad. I am now going to answer some more questions.
So we can take a few minutes if you have any last minute questions for Dr. Z.
Yes.
He would love to answer them for you.
I do. Thomas, are the subsequent filtration models, which we have a lot of filter, it goes along, it's designed to filter out the products of the decay. Are they cavity? Yeah, so generally the stuff we're studying will get all the way through before it decays. So that's okay. You are going to lose some, it's true, because it's a statistical process. Some of them will decay, but we don't really care about them anyway. So anything that's not the right charge to mass ratio isn't really going to make it through. The fragment separator can select 1 nucleus out of a million billion others. It's incredibly selective. It's good at filtering the junk, basically. Would the fantastic isotope be more stable or at least different with electrons? So with electrons, yes, it is a more complete atom, but it's also very difficult for us to study and accelerate and that kind of thing. So yeah, we remove the electrons because there are some experiments we actually do where it does have the electrons back on, but mostly we want to study the nucleus itself. If you want to study a nucleus with electrons, there's a whole nother kind of physics for it. It's called atomic physics. There's a lot of different scales of physics. Let me tell you, we got all kinds of things. Good one, Tyson. Jane, do you have to worry about exposure to radioactivity? We make radioactive material in the building. When we're running, it's 24 hours a day. We're making stuff. Now, something I didn't really mention was that all of this equipment is behind large walls of concrete. Generally, that concrete is at least 6 feet thick. So you are never standing next to that equipment, and you have 6 feet of concrete between you and the equipment. So it's really not a problem. I actually have a dosimeter something I wear when I'm in the laboratory. It's a little badge. You might have seen these before. And they detect radiation. They measure how much you're getting. Every 3 months, I turn in that badge. Now, of course, I haven't been at the lab a lot in the last year. I'm looking forward to going back. But when I was working there full time, 40-hour weeks, every 3 months, I would turn in that badge and they would find out how much radiation I got. I got less radiation working in the building than I would standing outside. So it's totally fine, is the point. We are incredibly careful with radiation exposure because we want to do a good job, obviously. All right. What advancements in detection mechanisms would we like to see come to FRIB? Oh, man. One of the most difficult things to measure is neutrons, loose neutrons, which we have done experiments where we did that, and we're pretty good at it. They're always building better detectors. Always, always, always. What would I like to see? I mean, I'm very excited about the ones we are building. We are currently building this giant new separator because, like I said, we're going to try to get fantastic nuclei that stick on a few extra neutrons, just like we think they do in a supernova. And we're trying to measure like how likely that is to happen, right? How many times is that going to happen as you go through an area with some neutrons? And that's going to be a really hard thing to measure, but we're building this really ridiculous new fragment separator to be able to do it. And I guess I'll have to get back to you because it's going to keep changing. That's one of my favorite things about the lab. Never gets boring. Are there any dangers to the linear accelerators? People do sometimes, I mean, we're making a lot of radiation, but this whole thing is, built and set up because we know it's going to, be tough enough to continue to operate. If it was fragile, then we wouldn't get a lot of research done. That's true. People often ask if an earthquake would be a problem. One great thing is we live in Michigan, so that's great. We're not going to have too bad of an earthquake. And we do actually have sort of vibration stabilizers. No, it's like isolated from vibration in the concrete. So so it's actually there because you don't want trucks driving by to alter your experiment. But that is a really nice thing. Any other dangers? I don't know. We built it. We've done a pretty good job building it. Should be in good shape. Are you able to easily generate nuclei that have excess protons rather than excess neutrons? This is a really important point. Yes. Let's see. Okay. So to date, if you look at the number of the various isotopes that have been produced, we do have quite a few proton-rich. I think the balance is a little bit on the proton-rich side. I think it's been a little easier to make a proton-rich nucleus. That's one of the reasons we're building FRIB, because we really want to expand that access out into because we believe that you can have way more neutron-rich isotopes of an element than you can have proton-rich. So of the number of neutrons, you can have stable and you can have a little fewer neutrons. Not a lot fewer, but a little. But you can have a lot of extra neutrons and still have a nucleus that sticks together. And that's the stuff we want to study. So that's what FRIB is for. How do you get rid of the isotopes you don't want? Okay. Okay, Tim, this is great. You have to clean the magnets. We are filtering out billions and billions of nuclei. I will now drop 1 billion nuclei. There they go. Yeah. So yes, we're trapping an awful lot of nuclei in the insides of these things, but it just doesn't, you won't notice an accumulation. You really don't. That's what's funny about it. Yeah, that is really not an issue. Fun question though. Is there a way to harvest energy from FRIB? Oh man, okay. We spend way more energy than we're ever going to get out. That is a fact. To run the FRIB accelerator will take between 15 and 18 megawatts. Well, that's for the whole lab. 15 to 18 megawatts. That's about 36,000 houses worth of power. A lot of power. So, and then that power goes into, making nuclei go fast. So we can't, we're not going to harvest any useful energy, but we are going to harvest useful nuclei. We make a really wide variety of rare radioactive isotopes. Not all of them are what we want to study. Some of them are useful in medical procedures. Lots of patients get injected with radioactive nuclei for PET scans and various things. And we are going to make them as a side effect of doing our research. So we are building, as far as I know, the first one ever, an isotope harvesting station. So we've got nuclear chemists who are working on ways to collect, useful medical isotopes in large enough quantities and that will last long enough, hours or days, that we can ship them off to a hospital or wherever, and they can use it on the patient. So that's kind of cool. What happens if you hit the nuclei too hard? Man. So we've talked about the LHC a little bit at CERN. They want to study basically matter at the quark level. We know protons and neutrons are made of quarks. They're just way, way, way smaller. So our lab studies nuclei. But if you hit a nucleus at like practically the speed of light, like they do at LHC or Fermilab or places like that, you don't have a nucleus left over. You've got quarks. And then they can study quark matter and how it acts. So basically, if we made our accelerator much, much more powerful, we wouldn't be doing nuclear science anymore. And that's what we want to study. So we're not. So it is actually too hard. The director of our laboratory once explained it to me like this. If you have a piggy bank and you want to see what's inside, you could use dynamite. But you would obliterate whatever it was that you were trying to measure. The money, I assume, inside. You'd rather use a hammer than dynamite. Our laboratory is a hammer, and the LHC is dynamite. And that's good for their experiments, but not for ours. Good question, A. Can you convert a neutron to a proton in a nucleus? That is exactly what happens when you have too many neutrons in a nucleus. When you make these really neutron-rich, fantastic nuclei in maybe a supernova or neutron-star merger, when they decay, it's called beta minus. Essentially, one of the neutrons inside changes to a proton, and then an electron comes out. So that's called a weak force decay. It's a long story. But essentially, if you've got a lot of extra neutrons, which means you have a lot of extra energy in the nucleus, then you're allowed to change a neutron into a proton and shoot something out. Holy moly, any more questions from Facebook?
Nope, I think we've made it through all of the questions for tonight.
That was intense, people.
That was awesome.
You pat yourselves on the back because that was awesome. Those were really good questions.
And as Dr. Z mentioned, he's got a few more things up his sleeve for the rest of the Science Festival. We have a big day Saturday with, I think there are like 50 different events on our virtual platform. So head to sciencefestival.msu.edu to check out our schedule. And if you're on our virtual platform and want to see all the live events, you can go to the webcast agenda.
Tons of options, tons of options.
Yeah.
One more answer for Anonymous. Can you alter the speed that you hit the carbon disk by turning on and off those accelerators? We're going to have 300 of those cylinders in a row. So yes, depending on how many of them are on, that varies the energy that you hit the target with. For our purposes, you want to hit with as many as you can, but we don't need to hit with all of them either. So that's a nice thing. Like if one or two of them go down or something, it doesn't really matter. When we had a cyclotron, if that went down, you're done. So that's an important point. Good one. Could you guys study both isotopes and quarks? We're not high energy enough really to do a really good quark research. So we're just studying. So there's atomic physics, there's nuclear physics, there's high energy physics where you're studying the quarks inside. There's solid state where you're studying larger materials. There's just tons of different physics. Technically, they should all connect because it's all related, but you know, we're just not that good yet. Maybe someday soon. How often do you have to do maintenance on the cylinders? Hopefully very little. They've actually set up locations with mechanical arms. They don't want people to have to go in there after it started running. So even when we turn it off, they don't want people in there. So they're going to be able to use a crane, remove one of the cryomodules, move it over, take the door off, and then get in there with the mechanical arms to fix stuff. Hopefully very rarely. Very rarely. But it's possible. Cool. Hey, tell your friends, FRIB, Science Festival. We got a virtual tour on Saturday, along with all the other things.
Awesome. And I think on that note, we will sign off for the night, let everyone get nice rest. And we look forward to seeing everybody on Saturday and then continuing on through the month of April. So there's something for everyone, we like to say. All right. Well, thank you, Zach. I learned something new every time I listen to your talk.
That's by design. Cool. Good night, everybody.
Good night, everyone.
Good to see you.
Bye-bye.